Dr. Zhao Qi is a QuICS Hartree Postdoctoral Fellow in Quantum Information Science at the University of Maryland. His research interests include quantum simulation, quantum computing, quantum resource theory, and self-testing quantum information. He received his bachelor's degree and Ph.D. from Tsinghua University in 2014 and 2018, respectively. Then he joined Professor Pan Jian-Wei's group at the University of Science and Technology of China as a research associate in 2019. After QuICS, he joined the University of Hong Kong as an assistant professor in the Department of Computer Science. And let's welcome Dr. Zhao Qi.
Thank you, everyone. Thank you, Guojin, for your nice introduction. And also thank the Hong Hai Quantum Group for giving me this opportunity to introduce our recent work. This work is about the quantum simulation with the random inputs. Here is our archive number. If you want to know more details about this paper, you can check it out. And this work is also presented as a contributed talk in this year's QIP. So you can also find the video in the QIP YouTube channel. This is joint work with the Zhao from NUS, Alexander, Andrew from Maryland, and Tong Yang from MIT and Peking University. Okay. And at first, I would like to give a brief introduction. Yeah.
Excuse me, Zhao, could you use the full screen of your slides?
Oh, from my screen, it shows full screen.
Oh, really?
Yeah, maybe. Sorry. I need to. It's weird. Let me share it again. Yeah, okay. It is full screen now?
Yes, it's full screen. Thank you.
Oh, okay. Is everything okay now?
Yeah.
Okay.
It's okay.
Okay. Sorry. Sorry for all this thing.
It's fine.
Yeah, okay. At first, I would like to give a brief introduction about background for the quantum simulation. And recently, we know the quantum computers and the quantum algorithms are very hot topics. And for the quantum computers, they can believed to solve some certain problem dramatically faster than some ordinary or classic computers. There are mainly two types of the quantum algorithms. Some algorithms, they could provide the exponential speed up, like the Zhao algorithm, or simulating quantum mechanics. People also call it quantum simulation. And also the solving the linear system of equations. For this exponential speed up quantum algorithm, it means that for some problem, we could use the quantum computers to solve it using the resource t, but we need a exponential function of t or super polynomial function of t to solve it using classical computers. Another type of quantum algorithm is about the polynomial speed up, like the Grover algorithm, amplitude amplification, and algorithm based on quantum work search. For this type of quantum algorithm, we could use the quantum computers to solve it with resource t, but we could use the classical computers to solve it with a polynomial function of t. Among all these quantum algorithms, the simulating quantum mechanics, also known quantum simulation, is one of the most promising application of quantum computers. This idea was first proposed by Richard Feynman in 1981, is to use the quantum computers to simulate the quantum system. And this problem is like sometimes we want to know some property or the evolution dynamics of a quantum system, but we can't have the direct access to this evolution. So we need some quantum simulators or quantum computers and encode the original problem in our quantum simulators. This quantum simulator much easier to implement or much easier to control, is programmable. Then by using these quantum simulators, we could solve the problem. We prepare some initial state, and make the evolution. And at last, we make some experiment to know the property of this state or this evolution. Okay, so with the current techniques, we know the universal quantum computers maybe is still extremely challenging, so we can't achieve it. But maybe the quantum simulator, it doesn't have to be the universal quantum computer. It could just be some special purpose machine which are designed to perform specific tasks, just like quantum simulator might be a more feasible option now. Here we may also don't need the error correction. Recently, the research all over the world, they have used different physical system to build the quantum simulators. Like NQ use an N-trap system to build a quantum simulator to simulate the water molecule. And Google and IBM, they build the superconducting quantum simulators to simulate different kinds of the different molecules. They can be seen as the first real-world applications of quantum computers. And why we need these quantum computers or quantum simulators to do something is because maybe for the physicist, chemist, or biologist, sometimes they have to simulate how the molecule and the atom to behave. But this simulation usually require a massive amount of computing power. So because the interaction between these particles, these molecule or atoms, they are quite complex. And also their behavior obey the quantum mechanics, which means that they have some uncertainty property, which make the classical simulation even harder. So even with the help of the most powerful supercomputers, the people can still only simulate the molecule with up to a few hundred atoms. So here, the quantum simulators can provide an alternative way to do that. It's because in these quantum simulators, all these particles, all these elements, they obey the quantum mechanics. So it's more natural to use the quantum simulators to simulate this quantum behavior. And with the help of this quantum computers, maybe we could develop the new next generation battery or improve the catalyst and design a new drug and also discover the novel superconducting material. We could also use it to simulate the molecule reaction in chemistry and simulate different kinds of the physics theory, like the quantum field theory, simulate some theory in black hole. And besides these applications, we could also use the quantum simulation to implement other quantum algorithms, like the adiabatic optimization and quantum walk or linear differential equation. For the optimization problem or maybe the linear differential equation problem, they can also have the application in some different kind of financial services. So that's why recently the JP Morgan, they also built their own team about the quantum team to develop the different kinds of quantum algorithm to solve the financial task. Okay, after talking about the application or maybe the importance of the quantum simulation, next I would like to give a more formal definition of what is a quantum simulation problem. People also call it Hamiltonian simulation problem. So Hamiltonian is a kind of a large Hermitian matrix describe the evolution, describe the energy of some systems. And in the Schrödinger equation can describe the evolution or dynamic of some physical systems. From some given initial state, percent 0, after a t time evolution, this state will be e to the minus ht times percent 0. It's another state. So here the quantum simulation problem is for some given Hamiltonian acting on n qubits and evolution time t, and also the predetermined accuracy or error epsilon. We can't have the direct access to this ideal evolution e to the minus ht. So we want to construct some quantum circuits U. This U is much easier to implement to approximate the ideal evolution with at most epsilon error. This is the Hamiltonian simulation problem. But this one we want these two operators are very close. A more practical or more feasible definition for this problem is we know our initial state. Maybe we only care about some certain initial state or maybe specific type of initial state. So a more practical problem is we know our initial state, and we only want to guarantee the output state for this initial state that are close. The output state are quite close. This is the second problem. Furthermore, in practice, maybe we only not just care about the output, the distance of output state. We also care about some observable. We want to know some observable. We want to know the expectation value for this observable. So a more practical version for this problem is we only want to guarantee the observable expected value for this observable is quite close. Okay, and the next problem is how to construct this approximate evolution, this approximate quantum circuits U. There are a lot of different ways to do that, like the variational quantum algorithms, like analog quantum simulation algorithms. But today I will just mainly focus on the digital quantum simulation algorithms. In this digital quantum simulation algorithm, we also have two types of quantum algorithm. The first one is called product formula method, also known as the Trotter or Trotter-Suzuki method. And this one is quite direct, and we implement the different type of the evolution one by one. So we call it product formula method. We have the first order product formula method and second order or high order product formula method. Recently, we also have some modified version like the randomized Trotter method. The second type of digital quantum simulation algorithm is based on the linear combination of unitary. It's called LCU. In this type of algorithm, we have truncated Taylor series method and quantum signal processing method. For this two types of algorithms, they have the different advantage in different field, in different region for different problem. Okay, but for most of this algorithm, people in the error analysis, most of the results is about the worst case error analysis. It means that for the ideal evolution U0 and the approximate one is U, we want to know the spectral norm of the U0 minus U. It corresponds to the worst case input. That's why we call it the worst case error. And this U can be approximated by different algorithms. So, but in practice, sometimes our input states are not some worst case inputs. Our input states are just a small subset of the whole Hilbert space. It is some state with the unique physical meaning, the physical state, like the computational basis state, or state low energy input state, or maybe different kind of easily prepared state. If we use this worst case error analysis, this state could be far from our real initial state. Then we overestimate the error and overestimate the required resource for this quantum simulation task. And recently, a lot of effort have been made to explore different kind of input state. Like we know that for the low energy input state and the input state with the fixed electron or spin number. If we also consider some observable, like a local observable or fixed observable, we could have further improvement. And here in our work, we provide an alternative way to quantify the error in the quantum simulation. It's about the average case error. We want to know the average performance from a given ensemble. We randomly choose the state psi I with a probability pi. Then we want to know the average error for this ensemble. Here, the distance of the output state can be quantified by different distance measures like L2 norm or trace norm. And we can't solve this problem generally. Yeah, we need some condition or assumption about this ensemble. A very natural way to do that is we could assume this state, all the state are uniformly chosen from the whole Hilbert space. It's called hard random unit, hard random input state. But in practice, the hard random states are it's quite challenging to realize it. Maybe we could make this assumption or condition milder. It's like the T design input state. It means that for the sum of the T copy of the state can't be distinguished between the hard random integral of the T copy of the state. this definition of T design. And in this different design, the one design is the weakest assumption. It's the largest subset. It's much easier to realize. For example, if we know some input state like the 0 state, then we implement the random unit array on each qubit, just a one layer circuit. Then this output state is one design state. Another example for one design example is the uniform distribution over orthogonal basis, like a computational basis state. We choose the state 0, 0, 0, 0, 0, 1, or 1, 1, 1 with the same probability. Then this example is a one design. So in the following of this talk, we will just mainly focus on the one design input state. And this one is quite reasonable and much easier to realize. Okay, and here is the main result in our work. We mainly consider about the L2 norm for the distance. For the other type of the distance, like the trace norm or some other thing, the analysis is quite similar. We consider one design input state, and we gave the general results and related this error to a Frobenius norm. And we also consider different algorithms, like the product formula method and the LCU method. But for this product formula method, its total gate complexity is a polynomial function of 1 over epsilon. But for the LCU method, the total gate complexity is the log function of 1 over epsilon. In our work, we just kind of changed the epsilon. We changed the definition and changed this epsilon. So in this second type of algorithm, like LCU method, because it's a log function, so even you change this epsilon, but your improvement could only be mild. So in this work, we will just mainly focus on the product formula method. Okay, and we consider different type of Hamiltonians, and we can say different degree of improvement. And we show some interesting destructive error interference in the first order product formula method. At last, we consider some application of our result. We use this result to analyze the Trotter error in the OTOC problem. Okay, in the following, let's say the different all this result one by one in more details. Okay, up to now, do you have any question for this? Okay,
no, I think it's very clear. Thank you.
Okay. I have no question. I will go on. We want to know the average performance for this different for the L2 norm, and for at first we use the call chain inequality to make the because here the L2 norm is kind of the square root of this this variable s, and we can't directly estimate this one, so we need a call chain inequality here, then make the square roots out of the summation. Then we can estimate this one expectation value at first, then have the square root. So our result is like this average performance could be bounded by the Frobenius norm of the multiplicative error. Here, the multiplicative error means that for the ideal evolution U0, the approximate one is U. Then this M is a multiplicative error. So this average performance is bounded by the Frobenius norm of this one. And you can compare this with the worst case error. In the worst case error, the error is bounded by the spectral norm of this M. It means that it's the largest eigenvalue of M. But here, the Frobenius norm is kind of the root mean square of the eigenvalue of this operator M. So that's the difference. And we also show that it's a concentration result. We also show that if the input state is satisfied to design, then we could also upbound the variance of this variable. Then this upbound is also related to the Frobenius norm of the multiplicative error. So if this multiplicative error is very small, then it means that with a high probability, your performance should, for any chosen input state, your performance should be close to this average performance. So that means that maybe the average performance is more representative quantifier in quantum simulation. Okay, let's say how, so the problem now is how to estimate this from business norm of this multiplicative error. Let's say that the product formula method. For this method, we have let's say a simple example. If the Hamiltonian H equals A plus B, then in the short time evolution, in the short time X, the ideal evolution can be approximated by this one, first the evolution A and evolution B. The error is related to the commutator of A, B. This is the shorter decomposition. But in a long time evolution, at first we need to divide the whole time evolution into R slices. Then in each segment, each slice, we implement a different shorter approximation. Like the first order is implement the evolution A first and B, and second order is A and B and A. For the high order shorter method, it can also be defined recursively with a different. So with a 2-case order product formula method, we totally have 2 times the n to the power k minus 1 stage. Here, 1 stage means for example, if we have L terms, then the first order is the implement H1 to HL. The second order means H1 to HL, then HL to H1. So this is the 2 stage. Here, the stage means that we need the repetition of this way. Okay, and in the series of a shorter error paper in 2021, they show that this error can be upbounded by some spectral norm of the commutators. In the first order, this one is just the spectral norm of commutator A and B. But for the high order shorter method, and this error is the t to the power p plus 1 over the r to the power p, but times another parameter. This parameter is related to the commutator. It's a summation of different kinds of the spectral norm of the nested commutators. There's a nested commutators. Okay, this is the result for the shorter error. It's the worst case error analysis. Here we show that for this general piece order product formula method, if your input state satisfy one design, then we could also upbound this error. For this error is also for the t scaling and the r scaling, they're the same. They're just the t to the power p plus 1 over the r to the power p. But here we times another parameter, another operator, this TP. For this one, is a summation of different kinds of the from business norm of the nested commutators. Recall that in the worst case, this operator is kind of the spectral norm, but here is the from business norm. That's a difference for the average performance and the worst case performance. And we also show that here we just gave a symptotic scaling, and we also gave a more concrete prefactors for the first order product formula method and the second order product formula method. In this Titan one, we could remove some summation out of in the previous results. All the summation are out of the from business norm. Here in the Titan one, we make some summation into the from business norm. Then they can have me make this bond tighter. For the second product formula method, the result is also similar. Here I didn't show it here. It's quite complex. Here we call them the triangle bond. That's because in this error analysis, we first analyze the error in one segment, I mean the small time evolution, then use the triangle inequality, we upbound the long time evolution. So that's why we call it the triangle bond. The error may grow linearly with the number of segments. Okay, yeah. Here I may introduce some main techniques for this works. I'm not sure the time whether we have enough time. Maybe I could quickly go through these details. Yeah, it's about here in the first order charter, the multiplex of the arrow can be expressed as the two layer of the integrals of some operators. This operator is a commutator A and B. But here in our case, we want to know the trace of the m times m dagger. That is kind of a trace of the different integrals and some unitary times the commutator times another unitary times the commutator, right? And we could use the Cauchy inequality to upbound this one. Then we could remove this unitary P and Q and make it make this upbound is related just from Frobenius norm of A and B. So that's the kind of key technique we use here. So the key problem now is how to estimate this from Frobenius norm of the A and B. Right. Let's say a simple example for this problem. The most standard or most well-known example in the Hamiltonian simulation is n-qubit Heisenberg model. It's a nearest neighbor interactions. So it's a 1D interaction. And we could divide all these terms into two groups. One is the A group, is all the terms with the kind of the even label at the first qubit, and the B term is the sum of the different terms with all the this one is the even label. This one is the odd label. Yeah, for these two different A and B, this is called the even or odd pattern. Then this is the A and B. Then we want to estimate the commutator A and B. In the most of the original our analysis for this problem, people show that people take each terms into account. Then this error is kind of related to the for the spectrum of A and B is related to the n square. But in the serial Charter's paper, they show that this one can be tightened to the linear with n. N is the number of qubit here, right? So it's already the best known result for this worst case error, and people can't improve it anymore. But we could change the problem. Like if we change the input state, not the worst case input, but the low energy input, we could have the scaling could be the n to the power 2/3. In our case, we will show that if we only consider the random inputs, then the result is square root of n. So we have a quadratic improvement with respect of parameter n. Okay, next we will show that why we have a quadratic improvement with respect to number of n. That's a difference between the gap between the Frobenius norm and the spectral norm. If you just look at this operator is just a Pauli operator x, then they don't have a difference. The spectral norm and Frobenius norm are the same. But if this operator have, for example, have n terms, is the sum of the xi times xi plus 1, then in the trace of C times C dagger, we totally have the n squared terms, right? But in all these n squared terms, when the I equals I prime, this one is kind of identity. Then its trace is D is dimension. But if the I doesn't agree if the I prime, this one will change to another Pauli string. Then its trace is 0. So here, even we have the n squared terms here, we only have n terms make the contribution to this total trace. So that's why we will have the improvement when we consider this Frobenius norm. In this case, our Frobenius norm just the square root of n. So that's why in this nearest neighbor Heisenberg model, we could have the quadratic improvement. But when this operators say are more complex, then we could have the more significant improvement. Okay, so let's say some numerical result for our theoretical predictions. We also consider this lattice Hamiltonian, the n-qubit Heisenberg model. We use the even and odd pattern. Here we fix the t evolution time t equals the number of qubits, and cite the error this one is. Then we want to know the minimal Chiltern number to achieve this accuracy. In the second order product formula method, you can find that here the numerical result is the hard random one, is the blue dotted one, and the purple one is the worst case one. So they have quite different scaling. The average case is much better than the worst case. For our theoretical prediction is the green one. So the scaling could match that of the empirical result very well. This is for the result for the second order product formula method. But in the first order product formula method, we find a very interesting phenomenon, which is this one is the empirical results. This one is our triangle bond, our theoretical prediction. They have a huge gap. So this means that maybe in this case, the error doesn't grow linearly with the number of segments. We should not use the triangle inequality here. Okay. And so then we tighten this result and show. Here we also show some more numerics. If we use the triangle bond for the error, you would say that this error should be the square root of n times t square over r. So here is t square. But in our another numerical results, you can find that this error it's not a t square. It is a t at first, but after some point, it becomes a t cube. It's quite different with the triangle bond. So this means the triangle bond doesn't work. And here in the following, we'll introduce our tightened result. It's called interference bond. In this interference bond result, we could tighten it to the t over r plus t cube over r square. For the parameter n, they're the same with the triangle bond, but have different scaling with the t. For this one, you can see that it can match this numerical result very well. It's the linear with t at first and then become t cube if we fix the r and n. Now let's say a more formal expression for this interference bound results. If the Hamiltonian is the Hessenberg model, and A is odd terms, B is even terms, if an additional assumption is satisfied, then we could show that the average error is descaling. So the similar same phenomena also happened in the worst case error analysis, in this distractive error interference paper. Here we found a similar thing in the average case error analysis. And after this revision and this tightening result, this orange one is the tightened bond. It's called interference bond. So this scaling could match that of empirical hard random result very well. And note that here we use the hard random input because our result is more general than that. Our result can be applied to the one design input. But in the numerical result, you can find that the hard random one design or different kind of random input, they are quite similar. So we don't need, so this one you can also understand this for the one design input. They don't have much difference. Okay, and the main techniques here is maybe I don't need to tell more details about this result now. Okay, we also consider different kinds of other Hamiltonians. In the other previous result, we just showed the Hessenberg model, the lattice Hamiltonian. We could make our result more general, like the K-log Hamiltonians. It means a lot of terms. For each term, it acts on at most K qubits. And we could give the result for this one. We define some new induced norm for this Hamiltonians. But this results, let's say a simple example for this result. If all the terms is the spectral norm is smaller than 1, then you can say that in the worst case error, we know that the K-local and for the product formula first order and second order, this is the average case error for the first order and second order. In this both case, we both could have the n to the power k minus 1 over 2 scaling reduction. So it means the one the k is larger, then our reduction is more significant. And another special case for this k local Hamiltonian is the here we just show the scaling of n. For the other parameter t and r, they are the same both in both the worst case and the average case analysis. Okay, so we also consider another special example for two local Hamiltonians. It's called power law interactions. For these Hamiltonians, is the lot of terms for each term is spectron is related to the distance of the I and j. There are two sides on the lattice. In this case, this alpha, the alpha is very when this alpha is when this alpha is equals 0, it means that it's an infinite power law interaction. It means for two sides that are far from each other, but they still have the strong interactions. It's infinite range power law interactions. In this case, both in the first order and second order product formula method, we both have the square root of n reduction. Another case is when this alpha is quite large. It means the interaction will rapidly decaying. For two sides are far from each other, they don't have a strong interactions. In this case, for the asymptotic scaling, both in the worst case and average case, they are all the linear with n. So we don't have the improvement in this the asymptotic scaling. Okay, up to now, do you have any question about all the previous slides? Okay, then I will go on. We also show some numerical result for this power law interactions. We also consider in the infinite range alpha equals 0, and rapid decaying case here we consider alpha equals 4. Now for this infinite range case, these three curves are the second order product formula method, and you can say that our theoretical bound is the yellow one. It can match that of the numerical result, empirical result very well. And in the first order, we also can the theoretical results, both the triangle bound and the counting bound can match our empirical result very well. This is for the rapid decaying case. But in the infinite range, this is for the infinite range case, sorry. But for the rapid decaying case, the alpha equals 4. For the second order product formula method, all the results are very well. But for the first order product formula method, there's also a huge gap between this theoretical prediction with the numerical results. So this means maybe in this case, we also have some error interference, but we don't know how to prove it. So it's a kind of interesting open problem. Maybe in this kind of the Hamiltonian with 3 terms, not just the A plus B term, we also have the error interference, both in the worst case and the average case analysis. Okay, this is the other. Okay.
Is there any intuition and knowing that why the second order apply well for the rapid decaying case instead of the first order? Why the first order works badly? What is the reason? Intuition.
Let me think. The intuition between this one is the there are some explanation like in the first order it's a kind of A and B and D and B. So this pattern is quite similar to the second order. So maybe in practice you can regard this first order Chorter error in the second order way. So that's why sometimes the first order Chorter error, the scaling is similar to the second order. And the people we don't have a tight bound for the first order shorter method. That's because in the first order case, the error doesn't grow linearly with the number of segments. They have some interference. The error in different segments, they have some interaction, some different interference. So they will cancel some error out. Yeah, I'm not sure whether my answer addressed your problem.
So you mean in the first order approach, the interference is stronger, so they will amplify any interaction longer, right?
Sorry, you.
I mean, the first order case will amplify the interference. Is that
I mean, they will have some interference. I mean, the error, they will have some interference.
Okay, I see.
Yeah.
I mean, compared to second order, the interference is stronger. Okay.
Yeah. If I'm interested in this question, yeah, maybe I should show some slides. I just skip. Okay. For this one, it's give some more details about why we have the interference bound. It's because when we want to know a long time evolution error is the R, is a multiplicative error with the R segment. So this one can be approximated by the evolution, the multiplicative error in one segment and sum over something after some time evolution. And in this case, in each one segment, this error is the commutator B and A. But in this case, H equals A plus B. So this one can also be transformed to the commutator H, A, and B. Then this summation, we could convert this sum to an integral. Then in this integral for this one, it can also relate it to the sum to unitary. And then here we have a T scaling reduction. That is the detail for this proof. Yeah.
Okay, thank you.
Yeah, maybe I should go on for the last application for our results. In our result, we just showed some average input state if that is kind of the one design. But here we found that our result can also be applied to another problem. It's called out of time order correlator, OTOC problem. This problem is quite important in the quantum scambling and other, maybe the quantum black holes and other theory. I don't know. Yeah, this one is the two commuting local observable A and B. We want to know the expectation value B dagger T times A dagger times B dagger A. So this BT, this observable is the observable B after a time evolution. Okay. If we want to know this expectation value in the experiments, people can use this following circuit to measure this result. At first, we prepare some initial state. It's the phi tensor some identity. Then, so this one is according to the A dagger. Then we implement the evolution. It's the e to the minus IHT, and then the B, then e to IHT. Here we assume the B is unitary. After this evolution, and we perform the measurement on the first qubit, it's the measurement A. After running this circuit, we could know this observable. Here you can see that the input state is phi tensor some identity. So this one is not a one design or not a hard random, but you can understand it like we fix the first qubit, but randomly chosen the other n-1 qubit randomly. It's kind of the random input over subsystem. So our result can also be used to, in this case, in the random input over subsystem. Yeah, here why we need our analysis, because maybe in practice this evolution, you may also have the direct access to this evolution. So you need some algorithms, a promised one, to approximate this evolution. Then you will have the error here. By using the worst case error, this error is much bigger. But if we use our tighten one or average case error analysis, we could tighten this error, refine this error. So our result is about the random input out over subsystem. We can show that in this case, the average performance can be bounded by also the Frobenius norm of M, but over another normalized parameter. This normalized parameter, this dimension D, is related to the random system. In this case, this D is the n-1 qubit. So if this evolution is promised by the different kind of the product formula method, first order or second order, then we will have a different degree of improvement. And besides this application, in fact, in some other tasks like the trace estimation, like one clean qubit model, DQC1 or something, people want to know the trace of some unit ray. If this unit ray is also approximated by the Charter method, then our method can also be used to analyze this error. Okay. Next, about some of the Taylor series method, we also have some improvement, but as I have stated before, because the total gate complexity is the log function of 1 over epsilon. We only changed this epsilon, so the reduction for the total gate complexity is just mild. And here is the summary of today's talk. And at first, we gave some general results for the one design inputs. We know we could unbound the error for some Frobenius norm or multiplicative error. Then we consider different kinds of the algorithms and different kinds of Hamiltonians. We have different kind of the different degree of improvement. And we show that for the first order product formula method, we show the destructive error interference. Then we could tighten the results. At last, we also show our result to apply to the random over subsystem case. It can be used for the tighten the error in the OTOC problem. And note that here we also have another work. It's called concentration for Charter error from Caltech group. We have the similar results all about the random input state or the concentration for the Charter error. So if you are interested in this direction, you can also look at this paper. And here in the next step in the future, maybe we should also use our result to analyze the different other case like the imaginary time evolution, or maybe other case like potential function estimation, because they also have some trace of some evolution or trace of the e to the beta h. So maybe our techniques can also be used here. And here in our analysis, in the first step, we use a Cauchy inequality. We don't directly estimate the error for this average case. We use a Cauchy inequality, then estimate this bound. So maybe if we directly analyze estimate the error, not using the Cauchy inequality, maybe we could have a tighter bound, but we don't know for these results. And another interesting thing is about if we further consider some fixed observable or maybe random observable, we expect to have some further improvement or further gate reduction for this problem, for the random input state. And in the last case is about we show that our result can be used for the random over subsystem. Maybe it can also be used for the random over subspace, like the low energy subspace. If all the states is chosen in the low energy subspace, then what about the results? In fact, we have some numerical prediction. It shows that if we choose some low energy subspace, its scaling should also be the square root of n. So it's kind of better than the previous low energy subspace result, but we don't know how to prove it. Okay, thank you very much for this. I want to thank all my collaborators here, and thank you for listening. Do you have any questions for today's talk?
Thanks. Thank you, Dr. Zhao, to give us this nice talk. Is there any question from the audience?
Yes, I have one question.
Mm-hmm.
Yeah, like in one of the slides, you say that when you consider the rapidly decay power interaction, like the average case error and worst case error both have the order of n. So can I have some tuition, like kind of Hamiltonian system can have the improvement when we consider the average case error?
Yeah, here in this asymptotic scaling, they are both the ON. We don't have the improvement, but if you look at this numerical results, for this rapid decaying one, right? Yeah, for this one, this is the worst case, and this is the random case. So they still have the improvements. They are quite different. So this means that our analysis here in the asymptotic scaling is not tight. So maybe here it should not be just n. It should be maybe square root of n or some other thing, but we don't know how to prove it.
Oh.
Yeah.
Okay. So what do you think? What kind of factor can lead to this discrepancy, like between this is order of n and the other one is order of power? And
you mean the average case? I guess it could be the kind of the square root of n.
Oh.
Not sure. Let me say this this one, right? Maybe they. Yeah. Sorry, I think my answer is wrong. I guess the scaling, asymptotic scaling for both worst case and average case, they are both not tight. Yeah. So they both work well. Yeah, maybe
so
because
you mean that
average, because it's first order, they have some error interference. But our result, most of this result are just based on the triangle bond.
So here in this figure, you use what kind of method? You use the triangle bond, right?
Yeah, this the green one and purple one, the triangle bond. Yeah,
but why in the previous page is this order of n and this is order of n to the power of 2.64?
Oh, this because this scaling is the total scaling of the R. In the previous figure, we showed that we also have the different scaling for the T and R. Maybe you can say this. Yeah, here. In this table, we just show that the scaling of n. We also have parameter for T and R.
Oh, so you consider them together. Okay.
Yeah. In this numerical result, we consider all these things together.
Okay.
But you can find that that is not tight because here in the first order, if you use the triangle bond, then this one should be the n times the t squared over r. Then r, if t equals n, then r should be the n cube. But in this numerical result, it's not n cube. It's just the n to the power 2.6. Yeah. So it means we need some more tighten or refined error analysis for this power law interaction problem.
Okay. And I have another question. Like, can there's also some another Hamiltonian simulation like linear combination unitary? So can this kind of analyze like average error analysis can apply in on kind of Hamiltonian simulation method, like quantum signal processing or linear combination of unitary?
Yeah. We also consider average input in the linear combination of unitary method. As you said, that we have in this LSU type, we have the Taylor series and the QSP two method. Here we only try the Taylor series method, and we find that this problem may not be that interesting in this field just because it's the log function. We haven't tried the QSP method, but they are the same because they both have the log function for the total gate complexity. If you just change the average error here, you can see that, for example, in this case, in the worst case error analysis, this one is kind of the error is number of the terms is kind of OL, but average case is the square root of O. You have some improvements, right? But you should make this error into this log 1 over epsilon. Then in this one, you don't have a lot of improvements.
Okay.
So that's why we don't have a deeper exploration about the QSP method. Yeah.
Okay. Thanks.
Yeah, in fact, the similar thing, I guess, also happened in the low energy subspace analysis. They also mainly consider about the Trotter method, but for the Taylor method, truncated Taylor series method, the improvement is also mild. Yeah.
Okay. Thank you.
Thank you for your question.
Sorry, I have a question.
Okay.
I'm not sure if I understand correctly. What's the different usage of the one design bound and two design bound? Do they correspond to the product formula 1 and 2 separately, or they just correspond to random input? So what's
so you mean if we here we mainly first of all consider the one design input. If we consider two design or maybe three design, whether we could have the further improvement? Is that your question?
Yeah, kind of.
Yeah,
and what's their role there?
Yeah, that's a very good question. At first, we expect that if we consider more random, because the hard random is kind of the kind of uniform random, right? More random inputs, then we will have some better results. But here we find that it's not the truth. As long as it satisfies one design, then for all the expectation value, they are the same. For the one design, two design, or hard random, they are the same. The same for the expectation value. But another thing is about variance. We guess that if the input state like the certified two design or hard random, then its variance or some high order variance could be smaller. It means that they have the same expectation value for the average error, but more concentrate. Yeah, I mean, for the two design.
So they should not be the discrepant for the discrepancy of the case you mentioned earlier. I mean, because they all have the even higher order, they have the same expectation. So
yes,
yes. Okay.
They don't have the improvement if you have considered some hard random.
Okay, so usually people only consider up to two order or two in this case for constraint variance, in which case we need tighter variance.
I guess that if you just look at the expectation value, then one design is enough. Yeah, you don't need the design.
I see. Okay, thank you.
Thank you for your question.
Is there any questions from the audience? Okay, I think it is about time to finish this talk. And thanks, Dr. Zhao, to give us this talk. And that's thank you again.
谢谢谢谢 ，It's a very interesting talk.
那我先 stop sharing。
好，那我想我们今天的 talk 就到这边嘛。那我们找机会再多聊聊。